Data lake is a file sitting on S3 bucket, which you can use to run SQL query without even loading up into a database. That's it. So before actually I dig into the data lake, I wanted to go back and do a little bit of background on how the data lake and Lakehouse and all these concepts have evolved. So operational database pretty much came into around 70s where all these technologies like Oracle, Teradata, they have flourished during that time. It allows businesses and technologies to store the data into a database. And that time, the meaning of database was that you store all your transactional information. At the same time, you do all analytics job on the same database. There was a problem as the size of database and the volume on the operation grew during the business hour or whenever the database is really busy. When you run an analytics job, it will slow down the whole process. And it actually created a lot of problem that people started running on shifts. Example, whenever the business operation is running and you do the analytics job in the off hour, that was not very convenient. So how they solve this problem? By splitting the database into two types of database. What they call is a data warehousing. So your operational database, example, your Postgres or Oracle, could be a smaller database, very fast, and you keep a data reservoir in something called data warehousing, which will be much larger database, but it will have a lot of latency as well. Because users are very different for this data warehouse. You're not talking about the end customer interacting with the database. You're talking about data analyst person interacting with the data to doing some transformation. And data warehousing, as the size started growing up, it stumbled upon a lot of challenges. First of all, was the scalability, cost, and the same time, data lake came into the picture. Data lake became really popular with the Hadoop in 2010s. And that was the idea that you can take the same volume and size of data, but you can run on a distributed platform rather than a single one. And that is where the concept of horizontal scalability versus vertical scalability come into picture. But that data lake didn't solve a fundamental problem which data warehouse still solving, which was ACID. The transaction were not atomic. And that is where the Lakehouse architecture came along in 2020s. And this has been a really popular among enterprise. So there are twofold driver for this particular move. First was a technology evolution. As traditional data warehouses started moving in, they were very bulky and hard to scale. And the distribution, when it came along with Hadoop, you can actually create distributed computing, but it still didn't solve the problem of your atomicity of the data. And what happened was that as the cloud migration came along and data started moving in, the business model of running a data center changed from a capex heavy to opex heavy. In a capex model, a CFO or larger corporation, they will spend a lot of capital expenditure on a data center build out. They will amortize that over 5 years of period. However, when you are talking about a operational cost like AWS or Azure, the cost is OPEX and you are doing month to month. And that brings a lot of scrutiny from CFO and other groups asking the right question. Are we using the infrastructure the optimal way? Can we reduce the cost? And that is where the S3 base lakehouse architecture comes in. In this case, you are able to segregate your data and the compute in a such a way that you only pay for the storage, which is your S3, which is relatively inexpensive. And you use compute or pay for compute only when you need it. And that dramatically shifted the whole landscape of data. So data lake, or you can say the lake house architecture, is actually a kind of a inexpensive storage which can run on any engine. That is the key here. One storage, many engine. You store the data on S3, you can use Glue, you can use Athena, you can use Spark, you can use Redshift. Not only that, you can use any third-party tools like Databricks and Snowflake or anything of likes. And that allows you to do the biggest thing is you have a data lake or a lake, not a data swarm. That's what they talk about. And the lake house it provides you an asset transaction. What means that when you run a transaction, say if you are a bank or financial institution, you're writing it to the table, you have a guarantee that data is written. There is no half-cooked data. If you're doing a bank transfer, money has to be transferred full. It cannot do a half transfer. Those are some of the key features of asset transactions. Multi-engine support, it was never in the data warehousing because query engine and the data was always attached. Data lake unleash it, but you can see the Lakehouse architecture is kind of a taking all the good features of data warehousing and good features of data lake and combine into single one format. And the Lakehouse, how it achieves this asset transaction is using a metadata layer using Iceberg layer. In the Iceberg allows you to have a snapshotting, time travel, time versioning, and it allows you to have an asset transaction so that you can be sure when you're writing a data into a table, it is written and it is consistent across all subsequent reads. And everything, as I mentioned, is sitting on the S3. And the another aspect I want to highlight, the S3 based data is not a replacement, it is a complementary. So you still need your OLTP based database, which is your high, very low latency uh, write based workload data. And S3 you are usually using for mostly your data warehousing, which is schema on read, and you are keeping the costs really low. And you can attach with your CDC or any kind of other design patterns. Data ingestion. So data ingestion in S3, you can follow pretty much anything, but I have categorized into three way. One is stream, batch, and event. Stream, you're talking about a stream of data which is coming continuously generating data sources. You can think of a website clickstream. You can take an example of Apache Kafka-based ingestion. Batch data where is the bulk of the work happens in all the financial institution because all of them are running on a very batch way where you have end of the day settlement and you want to settle the transaction and the data is moved at the end of the day and following day analytics team gets the data and they do the processing. Event driven will be mostly your IoT based data and we will not be using for today's example. Today's example is based on the batch data. So here is a demo that we will be doing today, exactly end to end. Look like we will upload CSV file into S3 bucket and let it scan by glue. And then we will use Athena to query. And of course, we will do some transformation using ETL job as well. So let's get started. The first thing what I have done is I have set up my S3 bucket and strategically I have created three different buckets. There is a one extra you see, which is the Athena work. I'll explain it later. But for data lake perspective, all we need is a raw, which is a mostly input or a ingestion file location. And then you have a curated and we have a script. So raw file will all include the raw input file, which we are not supposed to change at all. So the reason for doing is that if in your data pipeline, you may be doing a lot of transformation of your data. If something goes wrong with the raw file, or maybe down the line during your transformation, you can always refer to the raw file. So that is the one of the rule of thumb, never touch the raw file. And then I have a curated repo bucket altogether. So let's take a look into the raw bucket. Raw bucket, I have this oil folder and I've already uploaded this file. You can actually simply just upload a button, click an upload button and upload it here as well. And remaining all other buckets are empty right now. And also what I've done is I've also uploaded the ETL script, which we'll be actually using to transform it. The ETL script and everything is in the GitHub repository, which I will be posting in the link below. And so you can refer that later also. Similarly, I have simply uploaded these files here. And the curated bucket is the bucket where once we do the ETL transformation, the file will be stored there and we will be using Athena again. I will be using glue one more time to crawl that particular file. Before we jump into this, let me walk through what exactly glue is. Glue is a serverless data integration platform which you can use for data cataloging. You can use it to run ETL jobs, and Glue Studio lets you do a lot of other things as well. The key feature that we will be using today is the crawler, ETL, and data catalog. So what it does is Glue reads the file from S3 and infer the schema. It doesn't make any decision, or it doesn't actually modify anything on the raw file. It just infer the schema from the CSV file, and sometimes it may be wrong, it may be good, but that's what we will do, multiple stages of transformation, so that till the point Glue is able to catch the right schema that we are looking for. So first round, we'll drop the file, Glue does the crawling, and it creates a data catalog. And this particular schema is registered into the table, a Glue table. And that table can be used by different Amazon services like Athena, Redshift, EMR to actually run the query. And then what we'll do is later on, we'll run a ETL Spark job, which will transform this particular file into something which is more user-friendly or data engineer-friendly, so that we can use that particular input file to use Glue one more time to infer the schema to have a better version of that particular table. So example, you can go here, the crawler is a little bit kind of hidden here in somewhere. So I have already created this crawler job. And before even you do the crawler, you need to create a database. So this database I've already created. This is called the Glue database. And this database doesn't really store anything. But this database is a meta store database. Don't confuse it with any other OLTP or any other database. It's just a meta store. It's storing the schema information so that any other engine are able to query. And whenever we run the crawler on it, the crawler will create tables into this particular database, and that table will be used by any other services subsequent, like shown here. And so example, I have this raw crawler. Raw crawler, I see, last time I ran it was successful. I can run it one more time. And you can see different parameters, a data source. In this one, I have given the data source as S3, and I've given this bucket. So what crawler will do, it will go ahead and always look for that particular table. So you can see certain parameters about the crawler. I have the name of it, S3, and you can actually edit anything. When you create this crawler, these all questions are asked, and this is why I'm showing you here. And then usually you need to create a new IAM policy, and I've already created it. And all the policy details, everything is in the GitHub repos. You can simply copy and paste it. And I'm giving this particular table also. So output will be written into this particular table. And I can simply run this crawler. I select this, say you might do this, and I can run it. It takes a little bit of time because it's kind of a batch process. And once the crawler is ran and everything, what it does is it creates the table, and I can use Athena to actually query it. So let me go to the right region. So you can see my database is already here. And here is the key thing which I want to show. You need to have the right work group for Athena to run the query. Because behind the scene, Athena uses Trino engine. So it needs certain infrastructure, even though it's a serverless, but it needs certain infra so that it can actually store its log and query and other details. So I can actually simply, and the biggest thing what I see here is that whenever the data has been created, say if I go to this table and I go to this raw table, and I can simply click this button, and AWS takes me to the Athena and the right workspace and everything, and also pre-populates the query. And I can simply fire this query to get the data. And you can see the raw file, as expected, it doesn't have any nice schema. You don't get a lot of information out of it. So in order to fix that problem, what we do is we will run another round of crawler. So I have created two crawlers, and this crawler is basically we will learn later on. So going back to our process, what we are doing, we are first time ingesting the file, running the crawler, creating the database, and then of course we made the query. And now we'll run an ETL job, which will take this particular plain file and transform into a well-partitioned file. So in order to create the ETL job, I can simply go to the Glue portal, and you can see I've already created one ETL file. And again, this ETL script is also available in the Git repository. So you don't have to actually worry. You can, all links will be provided. And this is what it does. It simply opens the file, CSV file, and is doing a simple transformation. And in this case, it's doing a partitioning of the table, partitioning by year, year and month. So this is a very common practice of partitioning the data. And one of the reason of partitioning data is actually to have a query performance, because whenever you have a partitioned data and you put a where clause, it actually improves the query performance, whatever engine that you're using. So I'll go ahead, and you can see probably I have already run here this job, or I can simply run one more time this particular ETL job. And again, as I mentioned, this ETL will take time to, because these are all batch process. It takes time. That's why I have already prepared everything. So that's running, and we have the data. So when we run the ETL job, it will do the transformation, and then we will run another crawler, glue crawler, which will, this is the one. This one will, you can see actually data source. This data source is not the it's not the base one. It is the curated folder. It is looking at that. And the ETL job, what it did, it took the file from the raw and put into the curated folder. And crawler, this new crawler will look at the curated folder in order to create a new table. So if I run it, as I mentioned, it will take time. It's already ran. And now this will create another table, which is my curated table. And same way, you can see the data type has been transformed from CSV to Parquet. And if I want to query the table, I'm able to simply go to the new table. And as I mentioned, AWS has already created everything for me, and I can simply have to run it. And you can see I have a much better rich schema that a data analyst person can use and do anything what they want. And few things before I conclude the session that I want to highlight a little bit about Athena. So Athena, a lot of people confuse between Athena, Redshift, and other platform. Athena is essentially a query engine. If you're coming from a Hadoop background, you can think of a kind of a Hive. So it allows you to have a serverless infra, so that which you can use to query your glue tables. And in the backend, they are using Trino Presto engine. And results are stored everything on S3. And that is the main beauty that I mentioned, that everything is stored in S3, so your storage cost is always really low, and you are paying for usage when you use. And one more point about Athena. Athena always, you see, it says how much data is scanned. And Athena is built based on how much data they scan rather than how much time it took. So that also makes you very clear, predictable expense that you're looking for from the cloud cost perspective. So as just to conclude it one more time, we had a raw file. We use crawler to create a table from the raw inferred schema. Then we use glue ETL job to clean that raw file into Parquet curated file. And once the Parquet curated file was created and dumped into S3 bucket, a new bucket, we again ran the glue crawler to create another table, which is the inferred table. And of course, this table is much more, it has a much more detailed schema. And then we again use Athena to query. So that was a quick demonstration of how you can build a simple end-to-end ETL pipeline, or setting stage for the data lake. And I hope you enjoyed this session. Everything I built here are linked in the everything I built here are provided into the Git repository, including the Terraform templates. So if you and your team is interested in learning more and want to do a customized workshop or training for your team, link is provided in the description, which you can reach out to me. Thank you so much.